Hello, Chem 2 students. I'm going to be sending out a Word document with an assignment, which will be due a week from today. And I'll go over some of the questions before I send it out. In question number 1, you're being asked to calculate the ratio of acetate to acetic acid. In other words, the ratio of base to acid that's needed to prepare this buffer. Okay, so you'd use the buffer equation for that. For part B, you'd also use the buffer equation. This time we're calculating the pH. In part C, this has to do with the effect of adding a small amount of base. I have a sample calculation of a similar problem. Let's say we have an acid with a pKa of 7.36 and the ratio of base concentration to acid concentration is 0.24 to 0.33. It turns out this is also the ratio of moles. So you can use moles or molarity, because whatever volume term you have in the denominator, say this is 0.24 millimoles per milliliter per 1 milliliter, and this is per 1 milliliter, the milliliter term would cancel out. So we can use this for either moles per liter, millimoles per milliliter, or millimoles. Okay, let's add 2 milliliters of 0.2 molar NaOH. Right, if I pick concentration times volume, I get 0.04 millimoles. This strong base is going to convert the weak acid to its conjugate base, A-, so that the amount of base will increase by that much, and the amount of acid will decrease by the same amount. So if we look at our log term, it was originally 0.24, we're going to increase the numerator by 0.04 since we're producing more base. We're going to decrease the denominator term by 0.04 since we're consuming acid. The log of that would equal negative 0.015, and so the pH would be 7.36 minus 0.015, or 7.34. Right, if we go to second page here, use KSP values to calculate molar solubilities for copper 2 phosphate. I've given you the KSP value, copper 1 bromide. And then question number 3, we're going the other direction. I'm giving you the solubility, and then you would calculate the KSP. Question number 4 deals with the common ion effect. Let's go back to this document right here. If I had lead chloride, for example, and I knew what the KSP was, I could solve for X, which would be the solubility. What if I had 0.03 molar lead nitrate, in other words, lead 2 from a different source? In that case, the common ion effect would involve this term, instead of being X, it would be 0.03 plus X. And then I would solve for x. I should be able to make an approximation that the x is small compared to 0.03 in that example. Okay, similarly, if I were to calculate the solubility of lead 2 chloride in a solution that had 0.05 molar sodium chloride. Okay, in that case, this term right here would be, instead of 2x, it would be 2x plus 0.05. And again, we should be able to make the approximation that 2x is small, and we could neglect that. Okay, so using the KSP, we would then solve for x, and that would be the solubility. Okay, so having a common ion is going to decrease the solubility. Okay, question number 4. Okay, will a precipitate of barium sulfate form when 100 milliliters of 4 times 10 to the minus third molar barium and 300 milliliters of 6 times 10 to the minus 4 molar sulfate form when those two are mixed? Okay, if you just say yes or no, there's no credit. Okay, you need to calculate the Q, and you would calculate the Q by first, okay, you would determine how many millimoles you had, and you would divide that by the total volume that you would get when you mix the two solutions. And you would compare that to the KSP. Okay, so you need to have an explanation. If you just say yes or no, there'll be no credit. Okay, number 5. Okay, for number 5, back up here. Okay, for number 5, okay, you have 40 milliliters of a 0.1 molar HCl solution. And what is the pH of the solution when 20 milliliters of sodium hydroxide is added? Okay, so what you'll need to do is, this is a 1-to-1 ratio, so you'll have to determine which one is in excess after the two solutions are mixed. Okay, if you have hydronium in excess, okay, you'll take the millimoles remaining and divide that by the total volume. Okay, and then calculate the pH. Okay, here, if we, okay, this will be the same concentration for the sodium hydroxide as for the HCl. All right, so if we add the same number of millimoles of sodium hydroxide as we have HCl, of course, that will be the equivalence point. Okay, and that should be easy to calculate. You know what the equivalence point is for a strong acid, strong base reaction. Okay, and then part C would be beyond the equivalence point. And so there you would calculate the excess hydroxide, and then from there find the pH. Okay, for part 6, okay, this is a weak acid, strong base titration. Okay, what is the pH halfway to the equivalence point. Okay. Remember the buffer equation. At the halfway point, your base concentration will equal the acid concentration. Okay, so number 7, benzoic acid. It will have 1.22 grams dissolved in 100 milliliters of water, 0.1 liters. Okay, calculate the moles. Okay, what's its concentration? And then you'll enter that value in the ice chart below. Okay, this is the pKa and the Ka. Okay, so you'll calculate X, and X will be the hydronium or hydrogen ion concentration. And you'll take minus the log of that to find the pH. Okay, part D. The amount of sodium hydroxide in millimoles that is required to neutralize the solution. Okay, remember that's that important equation that important relation that I talked about. Okay, we have a 1-to-1 ratio of sodium hydroxide to benzoic acid, and you calculated the moles of benzoic acid at the beginning. Okay, what is the pH of the solution halfway to the equivalence point? Okay, again, use the buffer equation. Your A minus is going to equal your HA. Okay, and then part F, if the solution in part A is titrated with 0.220 molar sodium hydroxide, what volume in liters or milliliters of sodium hydroxide is required to reach the equivalence point? That is to neutralize all of the benzoic acid. Okay, and then what is the combined volume? So that would be this volume plus the original volume that you started with. Okay, and then if you take the amount, okay, that is the moles of benzoic acid, or benzoate for that matter, that you used, divided that by the total volume, that will be your concentration of benzoate. Okay, so at the equivalence point, we've just converted all of the benzoic acid to benzoate. Okay, so that number is going to go into this ice chart right here. Okay, and then I want you to calculate the the Kb from the Ka. Okay, you were given the Ka earlier. Kb would be Kw divided by Ka. Okay, so this number that you calculated for concentration, okay, you're going to substitute that into here. Okay, you'll solve for X, which will be your OH at the equivalence point. Okay, since we're talking about a weak base here. Okay, and then from that, okay, calculate the pH. Okay, and you can take the OH, take minus the log, and subtract it from 14. That'll give you the pH. Okay, and your pH should be, since the resulting solution should be greater than 7, we're doing a weak acid with a strong base, it should be some number between 7 and 14.